Okay, sine of 1 over square root of n. You have to think about two things when doing the comparison. One is that you want to put something here. You want to choose your secondary series to compare with. And if it gives you a number, you're really trying to say that I know that this is similar to something else here when n is really big. And moreover, because we don't have much examples to use, these concrete examples that we know convergence of is not many. We just know the geometric series convergence, divergence, and the p-series convergence and divergence. So if you were to pick between one of these two, what would you pick? P-series or the geometric? Which one do you think is closer to this one?
The p-series.
Huh? The P one, right? Okay. So you think that this is similar to 1 over n to some power. What do you think this should be? 1/2? That's your hunch? That's a good hunch. But is that true?
No.
No? Yes? Well, okay. Do you remember when I did sine of 0.1 and I managed to figure this out by 5 correct decimal points? What was I using?
The Taylor series?
Yeah, I was saying that sine Taylor series is amazingly accurate for small values, right? So when you have some small value, say sine of x, when x is a small value, sine of x is similar to what?
To 0. To sine of 0.
Okay, well, no, sine of 0 is 0, but I'm just saying, how did I do this? Sine of 0.1. I said this is similar to something, right?
That's infinity from the, of 0 from the
No,
positive.
not helpful.
The limit is of 0.
What is sine x similar to? That's my question.
0.
Sine is not similar to cosine. I'm talking about the values near 0. I was able to do this. You remember that, right? What was I using?
It's just similar to 0.
I didn't say this is 0. Was that my answer?
No.
No, it wasn't.
Technically, that's true.
Well, it's, what do you mean by similar? Okay. All right.
X?
It's relatable.
Yeah, sine x is similar to x. Right?
You just replace
Why?
it.
Because what's the
Plug in the
Maclaurin
number.
series? Sine x is x minus
Minus 1,
over
2,
3 factorial, wrong,
3 factorial.
plus
1 over 5.
5 factorial x to the 5th and so on, so on, right? Okay, so if you truncate, these are approximations of the sign. Right? Now, even if you don't know Taylor series, you learn the following.
Wait, question?
Yes?
Isn't it x minus 1 and then minus 1 over 3 factorial?
Nope, it's not.
Okay.
What I wrote is correct. So even if you don't know Taylor series, we learned that sine x over x has limit as x goes to 0. What was the limit? 1, right? We learned that in Calc 1, right? Or you can also use L'Hopital's to differentiate top and bottom, get 1 as well, right? But what does that mean? That means that sine x over x is similar to 1 when x is really small. Now multiply x both sides. What do you get? Sine x is
X.
similar to x. Now, if you know that, isn't this clear? Right?
Yeah.
Sine of x is similar to x. Done. So once you have chosen your target to compare with, now we have to take the limit n going to infinity of sine of 1 over square root of n, 1 over square root of n, and then you take the limit as n going to infinity, which gives you Well, we're already convinced that this should be 1, but if you're not convinced, you can do the following. Set x as 1 over square root of n. Then, as n goes to infinity, x goes to where?
0.
Right? If you plug in infinity, you get 0, right? X goes to 0 plus. It's never negative, so it's 0 plus. So this limit will become x goes to 0 plus, and we decide to call these as x, right? We have sine x over x. Now that one we already know to be 1, either by L'Hopital's or something you learned in calculus. Okay. So since this is a non-zero value that converges, now we have to determine whether this converges or not. What kind of series is? Yeah, it's a p with p equals to
Less than
1/2. Does it converge?
Yes.
That's
Or,
p
sorry,
object.
no.
No, it diverges, right? This is,
This is less than 1.
yeah. And p is equal to 1/2, less or equal to 1, so diverges. And you can finally write down that summation of n from 1 through infinity of sine of 1 over n diverges by what test?
The limit comparison.
No, not p series.
The limit
We're applying this one, right? We use the p test for this. Okay?
Yeah.
Yeah, but how did we determine this, the convergence divergence of this? By a limit comparison test with the p series, okay? So here you have to say diverges by limit comparison test.
Would you have to explicitly show the p-series one? Like, would you have to write it out like that?
Yeah, you always have to state what p is. Anything that you forget to write, like the p-value, or you can also say. Well, if you have p, then I know that you use p-test, so that's fine. But if you forget to write limit comparison test, there will be points taken off. Okay.
So you only care about the end. You don't have to set up for the.
No, you have to first pick the correct one, or else you can't get the conclusion, right? Yeah, so that will be a big chunk of the points if I'm grading, and then I have to see the limit, how you do it. Some parts of the limit I'm sometimes not so harsh on it, because like a lot of people can just see this and already say that's going to 1 without going through this. Okay, so that's fine. But then you have to say p-test and the limit comparison test. Okay. All right, let's try this one. What's the dominant term on the top?
5 to the n.
N times 5 to the n. What's the dominant on the bottom?
N squared times 5 to the n.
What's this? If you simplify, what do you get?
1.
Just 1? 1 over n. Right? It's 1 over n. So that's the one that we want to compare with. Okay? Usually a lot of these are fractions. There's some exceptions. Sometimes it might be exponential. And because of that, just taking the dominant terms top and bottom can help you identify what to compare with. All right, so we're going to compare it with 1 over n going to infinity of n times 5 to the n plus 1 over 2 to the n plus n squared times 5 to the n divided by 1 over n. We're going to use keep change flip, so keep this one. And you flip 1 over n as n over 1. When multiplied, you get n squared times 5 to the n plus n over n. The bottom doesn't change at all. Now already you see that the dominant terms are n squared 5 to the n, n squared 5 to the n. They're exactly the same, so the limit should be 1. But if you want to be more rigorous, you can divide top and bottom by n squared. So we can divide top and bottom by n squared 5 to the n, divide by n squared 5 to the n, so that the end result is that limit n going to infinity. Anything divided by itself is 1. N divided by n squared is 1 over n, and you're dividing by 5 to the nth power as well, so it's 1 over 5 to the nth power. 1 over n squared, 2 over 5 to the nth power, and anything divided by itself is 1. So you can see that these go to 0, therefore you get 1 over 1, which is 1, and that's not equal to 0. Oh, when using the limit comparison test, make sure that you write that not equal to 0. That's important. Okay. So now since summation of 1 over n diverges or converges? Diverges by p-test, p equals to 1 less or equal to 1. Right? The above series diverges as well by limit comparison test.